In this video, chemical equations, we're going to look at different examples, how we balance them, how we use them, and the type of information that they provide. So first, we really need to think about what is a chemical reaction. A chemical reaction is the recipe by which reagents, the things that you start with, are converted to products, or what they produce, the final material. So if we were to think about this in a general equation where we have A plus B goes to C plus D. A and B are reactants, and C and D, these are the products. A chemical reaction is similar to a recipe. We know that if you combine flour, sugar, chocolate chips, other ingredients, you can create a chocolate chip cookie. But you need to know the proportions by which you can do that. And so the other thing that's important is a balanced chemical equation. So if we think about our products, so we can think about where 2A plus B gives us 3C plus D, where the stoichiometric ratio, which I'm going to highlight in red, is the large numbers at the front of any equation. Now, two of these, which now are going to have blue, have only one. And so it turns out that we don't tend to include the number one. So we know that 2A plus 1B, so the 1 is assumed in this case. But the stoichiometric ratio is the relationship between reactants and products. What that means is we could say, if you have 2A, and we assume that you have a lot of B, how much of C should you get? So the ratio here is the ability to convert from 2A into an unknown amount of C. Or if you were to have A, how much C would you expect to get? And so the stoichiometric ratio will be covered in a later video. In this case, we're going to talk about what is a chemical reaction, how do we balance it, what are the different types, and what do they look like. So the other thing that we'll note is that all equations tend to come with states, where if we have 2A as a gas plus B, which is aqueous, gives us 3C as a solid, plus D, aqueous, where those states are S for solid, G gives you gas, L is liquid, and AQ stands for aqueous. And aqueous means dissolved in water, and we are going to get in depth into aqueous solutions, how they function, what they do in a later video. But a chemical reaction is just the arrangement of the different reactants and products. So here are some different reaction types that we're going to look at through these video series. Combination, two or more elements combine to form a single product. For example, A plus B gives you C, or if we have 3Mg solid plus N2 gas, that gives you Mg3N2 solid. So a combination is where two or more elements combine to form a single product. Decomposition is the inverse of combination, where a single reactant decomposes into two or more products. So some examples of that are C decomposing. This little triangle up here is a delta symbol, and it means with heat, to A plus B, or calcium carbonate solid, when you heat it up, is going to decompose into calcium oxide solid plus CO2 gas. So a decomposition is where a single reactant decomposes into two or more products. And those are easily identified, both combination and decomposition, based on whether you have a single product or a single reactant. So combustion, this is a reaction with O2 to form CO2 plus water. And so this is a burning event. If you were to light a flammable material on fire in the presence of oxygen, you will get CO2 and water. And so a general equation for that would be X plus O2 gas, and that's going to give you CO2 gas plus H2O. And this can be a gas or liquid, kind of depends on the component. So an example for that would be the combustion of propane, which is C3H8 gas plus 5O2 gas. And that's going to give you 3CO2 gas plus 4H2O, also gas. So a combustion reaction, in the purposes of these videos, is a single flammable material that can come as a gas or a liquid that is burned in the presence of oxygen that converts to CO2 and H2O. Now, in our world, in these video series, this reaction will go to completion. And so you will only get CO2 and water. Whereas in a general combustion reaction, you can get a series of byproducts. So the next one is an alkali metal. And so this is the reaction between group 1 and group 7. These are quite vigorous, and so you would have 2M plus X2. So where group 1 is the leftmost, containing things like sodium, and group 7 are the halides, and that would form 2MX. So for example, 2Na solid plus Cl2 gas is going to give you 2 moles of NaC solid. And so these are quite vigorous. The other example is quite similar, but a more general statement of any metal with a halide reaction. So metal plus halide, and that's going to give you some version of a ionic compound. For example, if you have 2 iron solids plus 3 Cl2 gas, that's going to give you 2 FeCl3 as a solid. So these are some of the different reaction types. By and large, in this video, we are going to use the chemical formulas and names to balance the equations or to create products. In later videos, we will talk about how you can combine compounds and predict what those products will be. So balancing chemical equations. A balanced chemical equation verifies that the number of atoms of one element on the reactant side is equivalent to the product side. If you remember the conservation of mass, we know that the number of cobalt atoms on the left has to be equal to the number of cobalt atoms on the right. So for the next part of this video, we're going to look at balancing different chemical equations. And so I'll show you a couple of different tricks, but the best way to do this is to look and analyze what you see on the left and is it equivalent to the right. So in this case, we want to balance this equation. The first thing you always want to do is ask, is this already balanced? So if we just look at the cobalt atoms, we can see that there's 2 on the left and 1 on the right. And so no, this is not balanced. So the way I like to balance equations is to write a list of the elements seen. So we have cobalt, oxygen, and carbon. And on the reactant side, we have 2 cobalt, 3 oxygen, 1 carbon. On the reactant side, we have cobalt, oxygen, and carbon. Now it's important that you write these in the same order so that you can easily compare them. So we have 1 cobalt, 2 oxygen, and 1 carbon. So the first thing that we're going to do is try to balance an equation. So the first thing I'm going to do is to balance the oxygens. Now, if we look on the left, we have 3 oxygens, and there are 2 oxygens on the right. there's no number that's going to give us the same value. So the first thing I'm going to do is try to make the oxygens on the left an even number. And I'm going to do that because this 2 right here says that it's got to be divisible by 2. So I'm going to put a 2 as a coefficient here, which gives me 4 cobalt and 6 oxygens. We haven't changed the carbon, so I'm going to leave that alone. So when we do this, on the right side of the equation, we now need to try to balance the oxygens. So I'm going to put a 3 in front of the CO2. So now I have 3 carbons and 6 oxygens. So we started with the complex ion because both the carbon and the cobalt on either side were single. So we can easily adjust those as needed. So now I'm going to pick a different color to go back and adjust. So in order to balance the cobalt from the 4 on the left to the 1 on the right, we're going to put a 4 here, which gives us 4. And we see that there are 3 carbons on the right, so we are going to put a 3 in front of that, which gives us this. So then we are going to rewrite, including the states, our balanced chemical equation, which is 2 CO2O3 solid plus 3 carbon solid, and that's going to give us 4 cobalt atoms as a solid plus 3 CO2 gas. And so this would be our final balanced chemical equation. So the steps here are to write out all of the elements that you start with, and then you balance by rotating back and forth across the 2. So let's look at another example. So in this example, we have sodium sulfide plus copper nitrate gives us sodium nitrate and copper sulfide. So a couple of things to note. If you can identify a compound, such as this nitrate ion, that is in the same arrangement on both sides, you can leave it alone in your balancing. So on the left side, we have sodium ions, a sulfur ion, copper ion, and a nitrate ion. And so we're going to leave the nitrate alone because we see it present on both sides. Alternatively, you can go ahead and expand that out into the nitrogen and the oxygen, but I find that that becomes a lot of elements to keep track of, where on the other side, we will have the same compounds. So on the left, we have 2 sodium, 1 sulfur, 1 copper, 2 nitrates, 1 sodium, 1 nitrate, 1 copper, 1 sulfur. So now we need to identify how these interact. So we're going to pick a second color. I'm going to go green this time. So the first thing I'm going to do is see if I can balance the sodium. So I'm going to put a 2 here. In this case, that gives me 2 sodium. And now this equation is balanced because the sulfur and the copper both already had 1. So all we need to do is to rewrite our balanced chemical equation of Na2S aqueous plus CuNO3 2, also aqueous. And that gives us 2 NaNO3 aqueous plus CuS solid. And so that would be our final balanced chemical equation. So let's look at another example. So in these 2 examples, in the first one, we're going to have to generate the compounds using their chemical names. So in this case, it tells us write a balanced equation including states for aqueous strontium chloride. So strontium has a 2+ charge. So it'll be strontium chloride 2. Whoops, that's not how we write that. So let's go back and erase that. Strontium chloride aqueous. And it's going to interact with aqueous lithium phosphate. So lithium has a +1 charge and phosphate has a 3-, so that would be Li3PO4, also aqueous. And that's going to create solid strontium phosphate and aqueous lithium chloride. So the strontium has a 2+, so we're going to get strontium 3PO4 2 solid, plus LiCl, aqueous. So in this case, we are now going to be able to balance this chemical equation. So we're going to have on the left strontium, chlorine, lithium, and phosphate. And we'll see the same elements on the right. So we have 1 strontium, 2 chlorines, 3 lithium, 1 phosphate. We have 3 strontium here, we have 2 phosphates here, and 1 of each of these. So the question becomes, which of these do we try to balance first? In my opinion, since we see this complex ion here with these 3 strontium and 2 phosphates, I'm going to start to balance that first. Because this compound is a 1-to-1, we could try to do that. But if we were to look at the 1-to-1 here, these are already out of balance, and so we're going to have to adjust for that. So I'm going to start with red this time. And so for the chlorines, we're going to start to balance the strontium. So I'm going to put a 3 here. So we're going to get 3 strontium and 6 chlorine. And in front of the lithium phosphates, I'm going to balance the phosphate. And so I need 2 of those. So we will have 6 lithium and 2 phosphates. So now both the strontium and the phosphates are balanced. So we can add a second color and put a 6 in front of the lithium chloride, which would balance out both the chlorines and the lithium. So now we need to rewrite our balanced chemical equation to where we have 3 strontium chloride, aqueous, plus 2 Li3PO4, aqueous. And that's going to give us strontium, 3 strontium, 2 phosphates, solid, plus 6 lithium chloride, aqueous. And in this series of videos, we are actually not in a place where we can determine, without other evidence, what the states should be. However, in later videos and later series, we will learn how to predict what they could be. So let's do one more example. So I'm just going to scroll this up to give myself a little bit more room. So we now have lead 2 nitrate plus potassium chloride gives us potassium nitrate plus lead 2 chloride. So we're going to do the same thing. We're going to write down all of our compounds. So we have lead, nitrate, potassium, and chlorine. Put them in the same order for the other side. And so we have 1 lead, 2 nitrate, 1 potassium, 1 chlorine. On the other side, we have 1, 2, 1, 1. So we can see that there are some adjustments that need to be made. So the question is, where do we start? So I'm going to start by attempting to balance the nitrates on the product side. So I'm going to add a 2 here. And when I do that, I have 2 potassium and 2 nitrates. And so when we look to the reactant side, I need to include a 2 to balance out both the potassium and the chloride. So I'm going to add a 2 here, which will give me a 2 and a 2. And now when we compare these, we can see that they fully balance. So we can just rewrite our balanced chemical equation. So we have lead, 2 nitrate, aqueous, plus 2 potassium chloride, aqueous. And that gives us 2 potassium nitrate, aqueous, plus lead 2 chloride, solid. And so when we look at this, we can see that this equation balances as well. There are very few tricks with this, but the biggest one is to leave grouped items together, and those are your polyatomic ions. So a polyatomic ion stays together. At this point, we don't see the nitrate turn into something else. So we can use that information to our advantage when we create different balanced equations.